So in example 5 here, we've got California averages 2 major earthquakes per decade, and y is going to represent the number of major earthquakes in the next decade. And we've got a cost function here. The cost of damages, it depends, of course, on how many earthquakes you have. And in this case, the cost is 2y squared plus 5y plus 10. So we want to find the expected cost. How much do we expect on average to pay in damages per decade for earthquakes in California? And also find the probability that the damages will cost more than $40 million. What's the probability next year that we will have to spend more than $40 million on earthquake damages? I guess not next year, but next decade. So let's find the expected cost first. The expected cost here, the expected value of the cost is the expected value. Well, we're given that the cost is 2y squared plus 5y plus 10. Now, what we're really going to use very, very heavily here is linearity of expectation. Expectation is always linear, so I can expand this out into 2 times the expected value of y squared. I can't bring that square out, but I can bring the 2 outside, and I can separate up the different terms. 5 times the expected value of y plus the expected value of 10. Well, the expected value of 10 is just 10, so there's not much to say there. Now, 2 times the expected value of y squared. I figured out in example 4 that the expected value of y squared was lambda squared plus lambda. That was in example 4. If you didn't just watch it, then you'll want to go back and look at example 4 and see how we figured that out. So I'm not going to recalculate that now, but you can go back and check the earlier part of the video on example 4 if you haven't just watched it. So this is 2 times lambda squared plus lambda plus 5 times the expected value of y. Now, since this is a Poisson distribution, that's 5 times lambda plus 10. And so this is 2 lambda squared plus 2 lambda plus 5 lambda is 7 lambda. Plus 7 lambda plus 10. So let me go ahead and work that out with lambda is equal to 2. The reason I'm using lambda is equal to 2 is because we've been told that California averages 2 major earthquakes per decade. So that's lambda is equal to 2 here. And so this is 2 times lambda squared is 2 times 4, so that's 8. Plus 7 times 2 is 14, plus 10. 8 plus 14 is 22, that's 32. So that tells me that my expected cost, the expected amount that I should average on spending on damages per earthquake per decade is, I guess this was in millions of dollars, so this is $32 million. $32 million. That means long-term, California can expect to spend an average of $32 million on earthquake damage each decade. So if you want to make some planning based on how much it would cost to retrofit buildings or how much it would cost to make up different earthquake safety plans, you want to budget that against the expected amount of damages, which is going to be $32 million. So I'm going to do part B of this problem on the next slide here, but let's just quickly check here that the expected cost here was the expected value of, well, we were given the cost function, 2y squared plus 5y plus 10. And so we expanded that out using linearity of expectation. Very, very useful to use linearity of expectation. So we had the expected value of y squared was lambda squared plus lambda. That came from example 4, so you can go back and watch the video on example 4 if you don't know where that came from. The expected value of y is just lambda. That came from, well, we proved it in example 3, but I also gave you the answer back in one of the first slides in this lecture. And of course, the expected value of a constant 10 is just 10. So then I expanded that out. I got 8 plus 14 equals plus 10. That was using the value of lambda equals 2 that I got from the stem of the problem, that we're averaging 2 earthquakes per decade. And that gave me 32 as an answer, and apparently our units here are millions of dollars, so we're talking about $32 million for our expected cost for earthquake damage next decade. Let's go ahead and jump to the next slide, and we'll find the probability that the damages will cost more than $40 million. So that's what we're going to calculate here in example 5. The probability that the damages will cost more than $40 million. We already found the expected cost on the previous slide, so we're already done with that one. So in this case, the cost function here, the probability that C is greater than 40, C is, let me just write that as C is greater than 40. I want to convert that into values for Y. So let's see how that works out. Remember, the expected cost, or the cost, was 2y squared plus 5y plus 10. And I want to see if that's greater than or equal to 40. I want to try to simplify this as much as I can, but it's not going to simplify terribly well. I'm going to subtract 10 from both sides. 2y squared plus 5y, whoops, I forgot my 5 there, 5y is greater than or equal to 30. Now, I want to figure out which values of y I'll be looking at there, and then I can find their probabilities. Remember that y is a whole number, because with Poisson random variables, you're always getting whole numbers. In this case, we're counting the number of earthquakes we might have in the next decade. So you're going to have a whole number of earthquakes. You can't have half an earthquake. So in this case, let's figure out which values of y might give us 2y squared plus 5y greater than or equal to 30. There's not a good way to solve that for whole numbers. So short of something better, I'll use trial and error. Let me just plug in some values of y. If y equals 0, we'll get 2y squared plus 5y is 0, which is not greater than 30. That certainly does not work there. Let me try y is equal to 1. We'll get 2 plus 5. Is that greater than 30? No, that certainly is not. Let's try y is equal to 2. 2y squared is 2 times 4, so that's 8, plus 5y is 10. Is that greater than 30? No, that is not greater than 30, because that's 18. So let's try y is equal to 3. 2y squared is 2 times 9 is 18, plus 5 times y is 15. 18 plus 15, is that greater than 30? Yes, that is greater than 30, because that's 33. So y is equal to 3 or higher. Essentially, if we have 3 or more earthquakes next decade, then our cost goes above $40 million. So we want to find the probability of having 3 or more earthquakes next decade. So let me try and calculate that out. Probability that y is greater than or equal to 3. If we have 3 or more earthquakes, we bust the budget. If we can have fewer than 3 earthquakes, then we'll stay under budget, assuming we budgeted $40 million for earthquake repair. Now, it's hard to calculate p of y being greater than or equal to 3. What's easier to calculate is to find the probability of it being less than 3. So let me calculate the probability of 0 or 1 or 2 earthquakes, and then I will subtract that off from 1 to get the probability of there being more than 3 earthquakes. Whoops, I should have written p of 2 there. So that's a 2. And so let me, now I have to actually calculate these probabilities. So let me remind you of the Poisson distribution formula. The Poisson distribution formula tells me that P of y is equal to e to the negative lambda times lambda to the y over y factorial. And in this case, our lambda is equal to 2. So that e to the negative lambda is going to be constant for all these terms. This is 1 minus e to the negative 2. That's the constant part. Now I'm going to fill in the different values of y, with 2 being lambda. So 2 to the 0 over 0 factorial plus 2 to the 1 over 1 factorial plus 2 to the 2 over 2 factorial. So this is 1 minus, I'll put e squared as a denominator there. And 2 to the 0 over 0 factorial is 1, plus 2, plus 4 over 2 is 2. So I get here 1 minus 5 over e squared. That's my exact probability that there will be more than 3 earthquakes, which means we will bust our budget of $40 million for damages. I did throw that into a calculator. I found a decimal. It worked out to about 32.3%. So if I'm worried, if I budgeted $40 million for earthquake repair in California, and I'm worried about the prospect of going over budget, I should be worried because there's a 30% chance, actually a little more than 30% chance, that I will go over budget, that I will have more than 3 earthquakes, which means that I will end up spending more than $40 million on earthquake repair. So let me recap the steps here. We're interested in whether C is bigger than or equal to 40. So I plugged in my formula for C here. There's my cost being bigger than or equal to 40. And that simplified down a little bit. 2y squared plus 5y is greater than or equal to 30. And then I was trying to figure out which values of y would make that true. That's because y is a discrete random variable. So we're not looking for a real number for y. We're looking for whole numbers for y. So I just, since there's not an easy way to solve that, I just used trial and error. I plugged in some different values of y until I figured out which values of y would make that true. And the first one that worked, so I was plugging these y's in here. The first one that worked, that made it true, was y equals 3. And of course, all the other y's after that will make it true. So I was trying to calculate the probability that y is bigger than or equal to 3. And that's not an easy thing to do directly with the Poisson distribution. Instead, what you want to do is calculate the probability that y is less than or equal to 3, or sorry, less than 3, which means the probability of getting 0, 1, or 2. And then you subtract it from 1. So I used my Poisson distribution formula. And in particular, I noticed that one of these factors is constant, so I factored that out right here. That's the e to the negative 2. And then the other terms, I was just plugging in the different values of y equals 0, y equals 1, y equals 2. And all of those gave me pretty simple numbers to simplify down. That's my exact answer, 1 minus 5 over e squared. But I got a decimal approximation as 32.3%. So that's the probability that there will be more than 3 earthquakes, 3 or more earthquakes in California next year. And in turn, that tells me the probability that my cost is going to go above $40 million in damages next year. So that wraps up our lecture here on the Poisson distribution, and that also wraps up our chapter on discrete probability distributions. The next chapter is on continuous probability distributions, so we'll be talking about integrals instead of summations. That'll be a lot of fun. I hope you'll stick around for that. In the meantime, you are watching the probability lecture series here on Educator.com, and my name is Will Murray. Thanks for joining me. Bye-bye.